So first, we're going to describe what Monte Carlo simulations are and that are used to evaluate complex probability problems for which no analytical solution exists. And then we'll use Monte Carlo simulations to simulate the distributions of functions of random variables and then finally we'll use Monte Carlo simulation to simulate both aleatory and epistemic uncertainty. And functions of random variables. So aleatory, again, is the uncertainty associated with natural randomness or natural variability. And then epistemic is uncertainty associated with things like measurement error or model error. So those are our learning objectives. And in our discussion of functions of random variables or derived distributions, we said, for example, we had that equation for the wave height. So z was equal to f over 1400 d v squared. And we said, okay, we can measure the fetch, the length of the reservoir. We can measure the depth of the reservoir or average depth. But the wind speed is going to be variable, right? So it's got that natural variability. So that's going to follow an exponential distribution with 1 over v naught being our average wind speed. Okay, so then we use the concepts and formulas for derived distributions to then estimate the distribution of z. So we had, we took our distribution of f of z and we plugged that into that formula, and then we ended up with a distribution for f of z. And so that looked something like this, and that was for a given value of z, we could calculate the probability of that value occurring as a function of our uncertain velocity. Okay, but what would happen if, oh yeah, and let me just write that out. So f of z is equal to, let's see here, 1 over 2 v naught square root of az exp to the negative z over a square root v naught, where a was equal to f over 1400d. So that was a constant. A was a constant. This is called an analytical solution. So we could actually plug it into the formula to calculate the derived distribution and then come up with an equation that we can actually use, right? Analytical solution, you can solve it for an equation, a usable equation. However, say f followed a normal distribution with some mean and standard deviation, and say d followed another distribution, maybe log normal with a mean and a standard deviation. Now, there is no way we could solve this because now we're plugging in 1, 2, 3 PDFs into this equation for z. And there's just no way to solve that. It's going to be kind of intractable. So this is when we resort to numerical simulation or Monte Carlo simulation. And the way it works is we would just simply say, okay, well, f follows this distribution, d follows this distribution, v follows this distribution. Let's take n equals 10,000 samples from each of those distributions. and then plug those samples into our equation for z. So z is going to be equal to, z is going to have then a distribution based on f of z based on 1400 f of d, and then f of v squared, something like that. So these are the distributions then that we're plugging into, and then we're going to spit out 10K z values, and then we'll get a, you can write a histogram or something like that of what z would actually look like. So that's in its most basic sense what Monte Carlo simulation is. It's sampling from distributions with parameters that have their own distributions. So each parameter has a distribution. We take 10,000 samples of each, and then plug those samples into this equation for z, and we end up with a distribution for z. Now there's one more level to this. And this is basically when we're dealing with MCS for aleatory uncertainty, natural variability. So you could imagine a situation where, okay, the fetch, it's not just one value, right? It's going to have a bunch of different values. So it's going to be kind of not quite, a little bit random. The depth, well, it's not just a pool with one depth, right? Because it's a reservoir, so the depth's going to have some variability. So you can kind of describe that variability with these distributions. But what about epistemic uncertainty, where maybe we're not really good at measuring fetch or measuring depth or measuring wind speed? So let's look at what epistemic uncertainty might look like. So we said V follows an exponential distribution with 1 over V naught as our parameter. F follows a normal distribution with mu F, sigma F. And then D follows a log normal distribution. Whatever, I'll just call it mu YD and sigma YD. What epistemic uncertainty says is, well, now we've got our aleatory uncertainty, but now we want to know, what if we have uncertain parameters within the distributions representing the natural variability of our Z. So we've got two levels of parameters now, and it's getting a little bit tricky. So we have Z is equal to F over 1400 dV squared. And we said that each of these parameters is uncertain with their own distributions. And now we're saying, okay, well, I'll just take V, for example. So V follows exp over 1 over V naught. So now we're going to say V naught is uncertain, and it has its own distribution. So V naught has a mean value, right? So mean V is equal to V naught, and then we're going to just call it the coefficient of variation is going to equal to some value. We'll just say CV. So now what we're going to do is we're going to do kind of two levels of simulation. we would first simulate a distribution for parameter v naught, and say v naught follows a normal distribution with a mean of 1, and then our coefficient of variation, and then we'll multiply that by the actual value of v naught. So the given value, or the estimate of the parameter, times some normal distribution that just has a mean of 1. So that'll give us a distribution for v naught. So we sample from that and take a bunch of samples from that distribution, and then we plug v naught samples into v exp 1 over v naught. And then that then plugs into z is equal to f over 1400 dev squared. So we've added an additional layer of simulation. So it's kind of a simulation within a simulation. So we'll go over what that actually looks like in R. But I just kind of wanted to introduce it to you before we jumped in. So we've got a distribution here, a distribution of v